All right, guys, as promised, here is the lecture for Thursday, February 20th. This is going to be covering Chapter 3, the second part of Chapter 3, and then we're going to go on into Chapter 9. So we're going to pick up right where we were at the end of Tuesday's class, talking about keys. Remember, we talked about on Tuesday relations, and relations have attributes. And then each individual instance of data within a relation is going to be called a tuple. So we can kind of use the terminology relation, attribute, tuple, or equivalent thing would be a table and columns with rows. So kind of meaning the same thing. So kind of going back into what we were talking about for keys. So remember we said that no two tuples can have the same combination of values for all their attributes. So you can't have two rows in a table that are exactly the same. So right at the end we were talking about this concept of a superkey. So a superkey is specifying that it's some set of the attributes of a tuple that two can't have the same value. So every relation has at least one superkey, and that's basically just the set of all attributes in that tuple. So a key is a more specific instance of a superkey. So key is a superkey with the additional constraint that we can't remove any more attributes from that key and still have some kind of superkey. So if we remove one more attribute, we would no longer have a key. So basically a key is going to satisfy two properties. So two distinct tuples in any state of relation cannot have identical values for all attributes in the key. So this could be, if our key is something simple like student ID number, two students can't have the same ID number. If our key is multiple fields, or multiple attributes, maybe two have the same same value for one attribute, but they can't have the same values for all attributes. So the second property is that it's a minimal superkey. So that means it's a superkey, and we can't remove any more attributes from that key and still claim that it's unique. So kind of the example I was just saying, if we did have a key that had two attributes and either of those two attributes could have duplicate values, but the pair of values will never be duplicated. Well, if we remove either of those attributes from that key, it's no longer unique. So I'm going to go kind of fast through these since you can replay them as many times as you want. And then just as you listen to this, it's probably helpful to jot down any questions that you want me to go back over on Tuesday. And if you want answers sooner, you can always email me as well. So now we're going to talk about a candidate key. So when we look at a relation schema, there may be more than one key. So a car has a license number and an engine serial number. So both of those are keys in that they're completely unique, and since these are both individual keys, they're minimal. We can't remove any more than one, obviously. So these are both considered to be candidate keys. So now we're going to talk about primary key. So if we have multiple keys that are candidate keys, one of the keys is going to be designated as the primary key of that relation. And when we make the schema for these, we're going to underline whatever that primary key is. So other candidate keys are just called unique keys. So they're other attributes in which the tuples have to have unique values, but we're not saying that it's the primary key that we're going to use. Oftentimes the primary key is going to be what I've hinted at for a while, where it's a self-incrementing value. But for something like student ID number, it may be generated in some other way. A good example is the driver's license numbers we have for Montana. They're a numerical combination of your birth date and all these other factors that end up being unique. Oops, let me jump back. So here shows a relation for a car, and we can see that it has a license number and engine serial number. So it has two candidate keys, and we're specifying license number as the primary key. Now, as you can tell here, there's no really any way to see on this schema that the engine serial number actually is a key. That's won't be apparent in the schema diagram of this. So relation database schema is going to be a design of the database. So as I just said, it's going to be a diagram. ER diagrams were with the circles or the ovals and the rectangles and all that. The relational database schema are going to be, it's going to look more like a table. Now, this is the same concept we've talked about over and over again about schema versus state. So relational database state is going to be a set of values that satisfy the integrity constraints. So whatever constraints are in place on the database, such as you can't have two values of a key that are the same, a set of values that is a valid for the database state is what we're talking about here. So we're going to look at two kind of definitions. So invalid state, that does not obey the integrity constraint. A valid state satisfies all the constraints. It's pretty obvious. It's either valid or invalid. Now, generally, invalid states, usually if you've set up your database design correctly and mapped all your constraints into your DBMS, you aren't going to be allowed to put it in an invalid state. But when we're talking about a theoretical set of data that could be put in there, it's certainly possible. So now looking at entity integrity constraint. So this is specifying that no primary key value can be null. So that kind of makes sense. If you're going to have a student ID number and say that's the primary key, you can't have some students that just don't have a key. Since the primary key is used to identify the individual tuples, there has to be a value specified for it. A referential integrity constraint, on the other hand, is specified between two relations. So this is maintaining consistency among tuples in two relations. So a tuple in one relation that refers to another relation must refer to an existing tuple in that relation. So to say that in more simple terms is if you have some kind of relation such as student and you have a relationship to another table that's major, if you're storing a value in the student table, that value, that tuple, has to exist in the major table. So if you're going to have a relationship between two tables, those values. So if I say Joe Johnson is a computer science major and it's referencing the major relation, that relation has to have a tuple for computer science in it, or it wouldn't be valid. So we call this a referential integrity constraint. So referential it's referencing something else. So we're going to specify referential integrity constraints using foreign keys. So this is something that's kind of been hinted at for a while in class. There's several rules about a foreign key. So the attributes in a foreign key have the same domains as the primary key attributes. So if, for example, major is specified that there's going to be a numeric number to represent each major, and we're going to store that number in the student table, the domain is the same. We can't say it's only numeric in the major table, but then say it's alphanumeric in the student table. That domain has to be consistent. So the value of a foreign key in a tuple either occurs as a value of a primary key for the tuple that it's in the relation it's related to, or it's null. So you can have a foreign key that's null. This is depending on the constraints you want to set up in your database. Sometimes can be desired, sometimes can be not. A good example of the student to major would be if you're undeclared. Perhaps you allow that foreign key that's referencing the major table to be null. In other cases, you may not want it. So how are we going to display these referential integrity constraints on a diagram? So remember, these are foreign keys. So we're going to have a directed arc from each foreign key to the relation it references. Now, arc, it's really looks more like a straight line, but arc is just kind of the term that we use when we're connecting those. So all integrity constraints should be specified on our relational database schema. So if it's the entity constraint, it's going to have the key, the primary key underlined. If it's a referential integrity constraint, we're going to connect each foreign key to what it references. And this process will appear as we start going into mapping of how. So there's also several other types of constraints we can look at. So the semantic integrity constraints. So we may have to specify and enforce these on a relational database. It is possible inside the database to use a concept called triggers and assertions. But it's more common to check for constraints within the application. This is kind of where we were talking about the business rules and that kind of thing. So like to make sure a phone number is a valid format, that kind of deal. Triggers and assertions, I've never actually used them in practice, but you can set up a rule where like a piece of data goes into the database and you have a trigger that says, well, when this happens, make these other changes to the data. It's something I'm not real experienced with, but it does exist and can be useful at times. So an example could be that the salary of an employee should not exceed the salary of an employee's supervisor. So you could set up a trigger to say if me, Dan Landy, works for Joe Johnson, and we raise my salary and it goes above Joe Johnson's salary, that we're going to automatically raise his salary to be equal to mine. So it's kind of a trigger saying my salary can't be higher than my supervisor's. Now, you could also do that in your application program by first checking what your supervisor's salary is and then either making another call to adjust it or to prevent entering a value that's higher than the supervisor's. I think this is an example where a trigger would be kind of weird, that you're increasing the salary of somebody else sort of automatically. You'd probably want to tell the user that Dan Landy's salary can't be greater than Joe Johnson's, which is this, and then force them to make an adjustment themselves. But I think that's where triggers both can be powerful but also dangerous because things are happening sort of out of your control. So this would be more of an assertion, is that the maximum number of hours an employee can work is 56 total across all projects. So you could have an assertion in your database that checks whenever those hours are updated to total them and make sure it's not over 56. Again, I think you'd more likely do this in your application program. For just a second. But this, sorry, it's a little weird when you jump back with this audio. So state constraints kind of specify what's valid. Transition constraints deal with the data's changing and how do we kind of put constraints on that. So you can see that an employee could get a raise or could get a demotion in pay. Well, that's still a valid state of the database. If you went from 30,000 to 25,000, that's not going to violate any state constraints. But if you have a transition constraint saying it can't go down, that would be a violation. So here's a possible database state for the company database. So remember, the schema is like the design, kind of the container, the state being populated with data. So you can see there's nothing in here that's invalid. If we look at the department, we have a department number. That's the primary key. There's no duplicates. Same for social security number. If we look at this department locations table, now this doesn't have the referential constraints connected yet. We'll see that on a diagram in a second, but you can kind of see that department locations has two attributes forming a key. So department number and department location. So we're storing that department number over in department as a foreign key. So actually, I said that backwards. Excuse me. We're storing the department number in the department locations as a foreign key. And you can see there's duplicates. There's 3 that have the valid or have a number 5 in the department number there. Department location, though, combined with the department number is unique. So if we look at those 5, they all have different locations: Bel Air, Sugar Land, and Houston. So the combination of those 2 together forms the primary key. Now, the constraint on a key that it has to, in order to be a key and not a super key, if we remove any more values, it's going to be no longer a key. We can see that here. If we remove department location, there's duplicates in D number. If we remove D number, there's duplicates in D location. So the combination of those 2 is the minimal set we can achieve. So here's another state kind of or it's not another state, it's just another part of the database. They've just put it on separate screens. So we can start to get a preview of how some of these things are going to evolve from our ER diagram. We have this works on, which is for working on a project. Dependent. These are all the things we've been looking at in the ER diagram. So this end kind of diagram here is an example of a relational schema with the referential integrity constraints displayed. So as you can see, as I was talking about the department locations table or relation, D number is a foreign key in department. So you can see the arrow points from the foreign key to the primary key. So that D number is appearing in 3 different relations: the employee relation, the project relation, and the department locations relation. And so you can see several of these are going to appear in multiple places. The social security number is used in 4 relations. So, and then do notice that, for example, SSN for social security number, it doesn't have to have the same name in the other relations. So it's ESSN, so like employee SSN. The name is irrelevant. We make the connection in the DBMS between the 2 attributes, and name is not important. So we're going to real quick just wrap up this chapter 3 discussion about different operations we can perform on the state of a database, and then what happens when we violate the constraints that we've put in place. So essentially, we can classify the operations we're going to perform on a relational database as retrieval or updates. So the basic operations that are going to change the state of relations are going to be insert, delete, and update or modify. Pretty much always going to call them updates because that's the SQL syntax. So insert, delete, and update map straight to the SQL that we're going to eventually start writing. Just jump back to the insert. So an example would be if you tried to insert a student into the student table that had the same student ID as another student. That would violate a constraint and throw an error. So the delete operation can really only violate the referential integrity. So the way this will happen is if a tuple is being deleted and some other relation is referencing it through a foreign key, that causes a problem. So for example, if I try to delete a department in the company database and that instance of a department is stored as a foreign key in a department location, that's going to cause an error because I can't delete the value that's being referenced. Now for the delete, we have several choices of what we're going to do if this happens. The first is called restrict. So that's basically reject the deletion. So the same kind of thing as on the insert, just throw an error and say you can't delete this tuple because something else is referencing it. Second option is called cascade. So the cascade defines that we're going to propagate the deletion by deleting every tuple that references. Now, we also have a third option is to set null. So anything that references what we're deleting, set the referencing attribute to null. Now, this depends on your database design, whether you allow nulls on that particular relationship. Now, I've never used the set null, but I've used the restrict and cascade significantly. For whatever reason in orbital shift, we generally have always just stuck with the restrict. So the problem with cascade is if you have a relation and then another relation related to that and then another relation related to that, so maybe you have a chain of 4 or 5 tables. Well, if you do the cascade and you delete at the highest part of that set of relations, you can wipe out a lot of data really fast. Now, that may be ultimately what you want to happen, but there's a certain risk. So it makes the coding easier because you can just say, delete this department, and then everything that references that department is gone. That definitely makes your coding quicker and easier, but with the potential loss of data. So when I did my database for this class of the cycle tracker, I used a ton of cascades. They work really nice. If I delete an area and it has routes and then all these rides that were tied to it, a cascade can really quickly delete everything. So it's just you got to weigh the pros and cons depending on kind of the context that you're dealing with. So then the third operation is the update operation. So in order to do an update, we're going to have to specify some kind of condition on the relation. So we're going to somehow determine which tuples are going to be modified. A lot of times you're going to just be modifying one tuple. So you're going to say update a tuple where the primary key is equal to this value. So you're saying give me this explicit one. Doesn't always have to be that way. You can do wider updates where you say update, say you had an employee of salary and say update every employee and raise their salary by 10%. So the updates can affect one or more tuples. If what we are updating is not part of the primary key and is also not a foreign key, usually it causes no problems. So I can update a salary pretty much across the board without causing problems. The only place I'm going to get into problems is if, for example, I enter a negative value. So that's going to kind of violate a domain constraint, but it's not going to violate any kind of referential constraints. However, if I try to update a primary or foreign key, we run into a similar set of issues as we do with insert delete. So if I try to update a primary key and I update it to something that already exists, if I try to edit a social security number and that one already exists, well, that's going to cause a problem. If I try to delete a value that's referenced in another relation as a foreign key, same thing. If I try to modify the value to something else, it's going to break that connection. So the update kind of has a combination of the issues of insert and delete, meaning you can cause all sorts of problems. Oftentimes, if you're using primary keys as like a self-incrementing field, you're not really ever going to update it. There really is no reason to. If it's something like student ID number, maybe, but kind of the same thing. A lot of times primary keys, there's just not a lot of reason to edit them. Foreign keys, that definitely comes up more often. Say I want to change departments to be in a different location, maybe that causes something problem with the foreign key. All right, so I know I kind of flew through that, but I want to get that information out there. Take a look at the textbook and jot down any questions you have on that. I think Chapter 9 is really going to kind of wrap together what we've learned about ER diagrams and about relational schema into one kind of nice package. We'll see how the two kind of connect. So Chapter 9 is basically about mapping ER diagrams to a relational database schema. So this is going to be based on a conceptual schema design. It's going to be a 7-step algorithm to convert an ER diagram into the relations. And then when we go to create our actual database in MySQL, these relations pretty much map straight into there. There's going to be an 8th step we'll look at, which is for dealing if you have an inheritance, if you're using an EER model. I'm going to go through that slide. We're not going to spend a lot of time on it, but just to be aware of, because I think the inheritance definitely has some power. So, as I said, there's actually a couple more steps, but the other steps are for concepts we didn't really talk about for EER. Okay, so just to kind of preview, this is the diagram we've looked at many times, though this one is specified with cardinality and participation constraints as opposed to min and max, but remember, it's essentially the same end result, just the structural constraints with min and max can have a little more specific detail. So we're going to go from that diagram to this. So this is the slide, or not the exact slide, but the similar image that we looked at in Chapter 3. So let's see how we... let's jump back. So really, you can make either side the primary key. We'll see an example in a second. It kind of just takes some domain knowledge to pick which side makes more sense. So step 4 is where we're going to have one-to-n relationships. So remember, this is like when we look at a department can have basically an unlimited number of employees. So many employees work for one department, kind of depending which way we read it. So for each of these one-to-n relationship types, or really it could be n-to-1, just depending which way you look at it, you're going to identify which relation represents the n side of the relationship. So in the employee to departments example, the employee is the n because multiple employees can work for one department. So you're going to include the primary key of the other entity type as a foreign key. So inside the employee relation, you're going to have a foreign key to the department relation. So whatever's on the n side is going to have a foreign key to the other side. Now, this step is exactly the same as step 3, only with the constraint that you can't just put the primary key and the foreign key on either relation. In this case, it has to be on the N side of the relationship type. So kind of the same thing. If there was attributes of the relationship, you're going to add those to the relation containing the primary key. Okay, I think I just stepped on my own terminology here. So we identify the N side of the relationship, which would be the employee. That relation is going to store a foreign key to the primary key of the other side. I think I just misspoke. So the employee relation is going to have a foreign key to the department. So if you have department of development, that has a key, primary key that's, say, a number. It could be 1. Each employee that works in that department is going to store a 1 in their like employee department number column. So the attributes of that relationship would actually go in the employee. So they're going to go still on the N side, but they're going to go with the foreign key. So I apologize. Ignore what I said at the. So step 5 is mapping M to N relationship types. So this is many to many. For each many to many relationship type, we're going to create a new relation. So 1 to many or 1 to 1 binary. In those cases, we're just going to do it with foreign keys to a primary key. In this case, we're actually going to create a whole new relation that we're going to use to connect the other two relations. So we're going to include in this new relation the primary keys of each relation. So say we redefined and said in our company database that an employee can work for multiple departments and a department can have multiple employees. So say we redefined that as an M to N relationship. We're going to have a new relation between the employee and department relation that we're going to call, say, employee per department. And inside of that relation, we're going to store the primary key from the employee table and the employee key from the department table. So the combination of those two foreign keys are going to form the primary key in this new relation. So the terminology gets tricky with these because you have primary keys in employee and department. You're storing those as foreign keys in this new relation. But together, those two foreign keys will form a primary key. So keys get pretty intertwined that way. So again, if there's any attributes of this M to N relationship, they're going to collapse into this new relation. So step 6 is mapping of multi-valued attributes. So for each multi-valued attribute, we're going to create a new relation. So remember, we're in a flat model. We can't have, say, for the example we've talked about with a car and its color. Well, it could be red and black, or instead of just red or black. So in the case where we have something that could have multiple values, we're going to create a new relation. And the relation is going to contain an attribute corresponding to the multi-valued attribute. So the example we're going to look at here is that department location, because remember, a department could be in multiple locations. So this new relation is going to have some attribute defined as the multi-valued attribute, and then a foreign key reference to whatever entity has the multi-valued attribute. So department number would be the case here. So the primary key is the combination of these attributes. So again, this is a case where a foreign key is going to form a primary key. So if a multi-valued attribute is composite, so if it's not only multi-valued but it has multiple pieces that form it, we include those in this new relation. So here's some examples of some of these mapping steps. So letter A shows just taking the employee entity and creating a relation out of it. That's very straightforward. Well, actually, it's employee, department, and project. Those were just regular entity types. B shows mapping the dependent entity. So remember, dependent was a weak entity type that was dependent on the employee to form a key. So the combination of an employee social security number and the name of the dependent formed the key. So it doesn't have its own key, but the combination of a foreign key of social security number and then the attribute dependent name together are going to form the key. C shows the works on relation. So was the example. An employee can work on multiple projects and multiple employees can work on each individual project. So it's an M-to-N relationship. So here we're storing... Sorry, my cat is jumping on here. Get out of here. So the works on is storing foreign keys to the social security number and the project number. So remember, it stores a foreign key to both tables that it's relating together. D shows multi-valued attribute. So we're taking the department locations. A department can be in multiple locations. We're making that into its own relation so that we can have those multiple entries. So step 7, last step, is mapping of n-ary relationship types. So for each n-ary, we're going to create a new relation. Now, n-ary is like ternary, those kind of things. We probably won't run into these a lot, but it works pretty similarly to many-to-many. But in this case, you're going to have primary keys of all entities of all relations participating. So if it's ternary, you're going to have the primary key of each of the 3 relations that are participating. And then again, you include the simple attributes. So this table kind of shows how we correspond between the ER terminology and then the relational. So on an ER model, an entity type, that becomes an entity relation. A 1-to-1 or a 1-to-N, that's going to be a foreign key. M-to-N is going to be a relationship relation with 2 foreign keys, then n-ary. Simple attribute just becomes an attribute. Composite attributes become multiple simple attributes. Multi-valued attributes on our models are going to be mapped into a new relation with a foreign key. And then the idea of a value set that we talked about in an ER model. So what's the set of values that are valid for an ER model? That's the domain in the relational model. And then in ER, we just had key. It's further defined in the relational model as a primary or secondary. So just be aware, in a relational schema, relationship types are not represented explicitly. So it doesn't really show up quite the same as it does on an ER diagram. We don't have a relation. We had a diamond for a relationship. In this case, these relationships are represented through primary and foreign keys. So the primary key in one table is stored as a foreign key in another. So 2 tuples are related when they have the same values. So if you have student ID number in a student table, and then you're storing that in a major table, for example, well, when you have the same value in both tables, that means they're related. So I'm going to just let you guys look at this step 8. I think this is something, there's 4 ways that they go through that you can map these inheritance higher, kind of complicated. I'd rather just maybe talk about this a little bit Tuesday. And then this just kind of shows On Tuesday also, I want to pick up with this example. So the remainder of these slides, I'd like you to take a look at them before Tuesday. These kind of show the individual steps of going through the company database, but also some other examples, and turning it into a relational model. We'll go through this example Tuesday, but please try to take a look before then. So I hope this worked out for you. I know I went fast, but we're looking like we're going to come in a little over 40 minutes. So review any parts you need, jot down any questions, and either email me if you want to answer sooner, or otherwise bring it on Tuesday and I'll answer it then. So hope you guys have a good weekend, and I will talk to you on Tuesday. Thanks.